Some covalent compounds have structures that can be drawn in more than one way, and we'll see that these are resonance structures. So if it's possible to write more than one possible structure with the same atom placement, if the structure contains double and or triple bonds and lone pairs, so these are electrons that can be moved around. One example is ozone, which is O3, which can be written with a single bond on the left and a double bond on the right, or it can be written with a double bond on the left and a single bond on the right. And this is not the same as just moving it back and forth. We've actually moved the electrons around, not the atoms though. If we look at ozone, it shows that while a typical single-single bond is 154, and a double bond is 134 picometers, the bond length in ozone is 144, so it is exactly in the middle of a single and a double bond, which means it's halfway between. To show resonance, we use this two-headed resonance arrow, which is different than a reaction. It just means resonance. So we draw the two structures, one with the double bond on one side, double bond on the other side, put the arrow between them, and what this shows is that the actual structure is a combination of both. Sometimes it's drawn like this with dotted lines to show half a bond on both sides, but this is pretty old-fashioned. We don't usually use that. It's not changing back and forth. It's an actual combination of the two structures. So the three structures for nitrate are drawn here. We can put the double bond in nitrate on the first atom, or the second atom, or the third atom, and move it around. We don't move the atoms around. The actual structure is a combination of all three, and it has a bond order of 1 1/3 because each bond is 1 1/3 bonds. To show the polyatomic ion, I put the whole thing in brackets, put the charge on the outside to show, I could have put brackets around each structure separately instead. It means exactly the same thing. Okay, the resonance structures for cyanate are a little bit different. The last ones, everything was equivalent. Here, I'm moving the bonds around, but these are not equivalent to each other. So I can put a triple bond and a single bond and a triple bond, or two double bonds, and then I have to move the lone pairs around. Everything still has an octet every single time. I could put each structure in brackets with the arrows, and it means exactly the same thing as the nitrate. Okay, formal charge gives us a way of figuring out which resonance structures make the most sense. The formula for formal charge is for each atom in the molecule, you look at the number of valence electrons and then subtract half of the bonding electrons plus all of the lone pair electrons. And the number that you come up with is the formal charge on that atom. The sum of all the formal charges must always be the charge on the molecule. So if it's neutral, they have to add up to 0. If it has a charge, all the formal charges have to add up to that charge. Okay, so we'll do water first. Draw the structure so you know how many bonds and lone pairs, and then do each atom individually. Oxygen has 6 valence electrons, and then I'm going to subtract half of the bonding, so there's 2 bonds, which is 4 bonding electrons, plus all of the lone pairs, and that gives me a formal charge of 0. Similarly, hydrogen is also 0. It has 1 valence electrons. It has 1 bond, so half of 2, plus no lone pairs equals 0. And then I labeled the structure with the formal charges. This can be useful later for figuring out which one is best. OH minus, which is the hydroxide, has this structure, and oxygen has a formal charge of 6 minus, 2 bonding, so half of 2, plus 6 lone pairs is -1. Hydrogen is always going to be 0. So this tells us that in my polyatomic, which has an overall charge of -1, the -1 actually sits on the oxygen. Stop your podcast and work through these and then check your answers. Okay, so the formal charges are all calculated here, so check your work, and then we label them on the molecule to see what makes sense. So in this next section, we're going to learn how to use formal charge to determine which resonance structures are the most important or least important. The rules are, we want smaller numbers. The closer you are to 0, the better the structure is. Don't have two non-zero charges next to each other, like a plus right next to a plus. That's bad. And the more negative formal charge should be on the more negative electronegative atom, if it's possible. So we're going to draw the two possible resonance structures for BFH2 and figure out the formal charges in both structures. So in the structure on the left, which puts a double bond between fluorine and bromine, we've got a +1 on fluorine and a -1 on boron, sorry. The one on the right, which violates the octet rule, but boron actually can do that, they have all 0 formal charges. So the one on the right is better for formal charges because everything is 0 and it's more stable. So work through the next problem, stop your podcast, and then check your work again. It's the NCO that we wrote earlier. Draw the 3 structures, figure out the formal charges, and figure out the best and the worst structure. Okay, the structure on the far right is the worst because it has a formal charge of -2, which is a higher number, and you want the numbers to be low. So that's definitely the least likely worst resonance structure. Of these two, which both have the same formal charge numbers, the one on the far left is the best because it puts a -1 on oxygen instead of nitrogen, which is more electronegative.